So, let us start with an example. Okay. We know that the following sequence omega c by pi sinc omega c n by pi. Okay. If this is x of n, this has got a discrete time Fourier transform which we have just now derived. This is the sequence that does not satisfy absolute summability, but square summability is satisfied. This is a sequence which is given by a rectangular function in the frequency domain. Write it as m equal to minus infinity to infinity rect of omega minus 2 pi m divided by 2 omega c. Okay. So, basically it is a rectangular function going from minus omega c to omega c and then periodic representations of that. Now, the task for us is to calculate the energy of the sequence x, which is summation n equal to minus infinity to infinity x of n magnitude squared. Okay. And we know that the we can get the expression for x of n. Okay. It is something which will give you a sign based expression, and again you will find that the expression is a monotonically decreasing function, but it is something that it will be very difficult for us to calculate in terms of the energy in a closed form expression. Okay. So, of course, I welcome you to try it. You can actually do a MATLAB experiment to try to approximate this energy over a large value. Okay. On the other hand, if you were to say, okay, rather than doing this, I am going to use Parseval's theorem. Parseval's theorem says that the energy in the time domain can be computed in the frequency domain as well. How can it be computed? You can 1 over 2 pi integral minus pi to pi minus pi to pi x e of j omega magnitude squared d omega over one period. Okay, so then you may want, it may be helpful for us to sort of sketch this function. This function has a height of 1 from minus omega c to omega c. This is magnitude x e of j omega. Okay, so then we say that, okay, this is very simple. This is going to be 1 over 2 pi integral minus omega c to omega c. The height is equal to 1, so 1 times d omega, which is equal to omega c divided by pi. So, you can write down the expression very confidently. E power x is equal to summation n equal to minus infinity to infinity x of n magnitude squared is equal to omega c divided by pi. Okay, so again you can see how powerful the Parseval's theorem is, something that would have been extremely difficult. You may have to approximate it, numerical approximation or numerical integration using MATLAB. You can write it in closed form in this manner. Okay, so again the Parseval's theorem is a tool that we use quite extensively and turns out to be very powerful in the applications that we are looking at. So, if I were to now go back and look at we can say that we have fully looked at the Fourier transform theorems. We have fully looked at the symmetry properties. So, it will be very helpful for us to do a number of examples and then move into looking at the Fourier transform theorems and complete that discussion. So, we are going to be looking at a number of examples. So, please look at the expression that, I mean, the examples that we're going to be working out, and also look at how we can apply the theorems or the results that we have studied so far, and we will be able to get the good understanding or the concepts reinforced from the examples that we're going to be looking at. Let us start by looking at a few examples which will require us to apply the properties of the discrete time Fourier transform that we have studied so far. So, first example that I would like you to try is to obtain the discrete time Fourier transform. Let us say this is example number 1, x of n is equal to 1 for all values of n. What is the corresponding discrete time Fourier transform? If you remember, we have already done something of this nature, and this is a result that we know for sure. So, we can write down saying this is equal to 2 pi summation. Basically, what you will get is the Dirac delta. So, m equal to minus infinity to infinity delta of omega minus 2 pi m. This can be omega plus or minus, does not matter. So, you can write it in both ways. So, this corresponds to a special case of the discrete time Fourier transform. Okay. Now, I would like you to look at the second example. The second example says that we are given that a power n u of n has got a discrete time Fourier transform given by 1 over 1 minus a e power minus j omega. We are given that modulus of a is less than 1. Okay. Now, what is the discrete time Fourier transform of minus 1 power n a power n u of n? So, there are two ways of doing this. Let us look at method 1. Okay, I will just write down method 1. Method 1. Method 1 says that there is a new sequence which is x1 of n, which is equal to minus a raised to the power n u of n. So, in other words, wherever there is a, you replace it with minus a, that is the new sequence. So, according to this approach, the Fourier transform, discrete time Fourier transform x1 e of j omega will be 1 over 1 plus a e power minus j omega. Am I right? And this is a correct method. Observation is a correct one, and we can also do the interesting experiment that we or the calculation that we did. We look at the response at omega equal to 0 and omega equal to pi. At omega equal to 0, you get a value 1 over 1 plus a, and at omega equal to pi, you will get a value 1 over 1 minus a. So, this is the value at omega equal to pi. Okay, and by symmetry, you can extend it beyond pi to this value. You can also extend it on the negative side, does not matter. You can go over entire period. This you can say is 2 pi. Okay. So, this is a high pass filter. A high pass filter. It allows high frequencies to pass through with gain. The low frequencies are attenuated. Okay. Now, of course, this is one way of doing it. The way that I would like you to visualize and do it is by the frequency shifting method. Apply the frequency shift property. Okay. The frequency shift property says that if you multiply by e power j omega naught n x of n, then what you will get is x e of j omega shifted by omega naught. Am I right? That is the frequency shift property. Now, if you look at this, minus 1 power n is the same as e power minus j pi n. Okay. So, this is a e power minus j pi plus pi minus pi does not matter. E power j pi n is a way to represent minus 1 power n. You can do a quick check to see that this is coming correctly. So, we now have minus 1 power n a power n u of n as represented as e power j pi n a power n u of n. Okay. So, then this says find out the original spectrum of the original sequence a power n u of n. We know that that calculation we have done. It looks like this. It goes from 1 over 1 minus a to 1 over 1 plus a. So, this height is 1 over 1 minus a, the lower value is equal to 1 over 1 plus a. It is a low pass filter. Now, if I multiply by e power minus j pi n, the corresponding e power j pi n a power n u of n is equal to the original discrete time Fourier transform shifted by pi. So, what we get is 1 over 1 e power j pi n. So, you will get 1 over 1 plus a e power minus j omega as the response. You can also visualize it without looking at this. You can say if I shifted this to by a value pi, what will it look like? So, if this is the place where it reaches the value of pi. Now, shifting this by pi will produce for you the sequence that looks like this. Okay. So, minus 1 power n multiplying the sequence is a very interesting property. Whatever was the original spectrum, it will shift it by a factor equal to pi. Okay. And this is one of the applications of the frequency shift property, which we always want to keep in mind, and also always be able to apply. All right. So, again let us keep moving forward in terms of our examples. Let us, what was the example number? Example 2. We are now on to example 3. I will need to copy this page before I use it. Edit, copy page. Right. Okay. Example number 3. Example 3. We have the following property that is in the differentiation property, right? We know that if you have a sequence x of n and this has a discrete time frequency x e of j omega, we know that n times x of n using the differentiation property. Okay, let us just make sure that we have that as a reference. The differentiation property says n times x of n is j times d by d omega of x e of j omega. J times d by d omega x e of j omega. Okay. So, if I were to tell you that I want to find out the sequence or the discrete time Fourier transform of n times a of n u of n. Okay, we have just now computed a of n u of n. A of n u of n has got a discrete time Fourier transform, which is given by 1 over 1 minus a e power minus j omega. Okay. Now, n times this will have a, you would have to take j times d by d omega of 1 over 1 minus a e power minus j omega. Okay, I am sure that you are very comfortable with the differentiation of rational functions. You know, it's called the u by v rule. You apply that, and please verify that this comes out to be a e power minus j omega divided by 1 minus a e power minus j omega whole squared. Okay, this is a application of the differentiation property. We don't need to do the calculation. We can straight away say that by applying the differentiation property, we have obtained this as the expression. Now comes the part 3b, an application. I want to find out the time domain sequence. What is a time domain sequence that will have a discrete time Fourier transform that is given by 1 minus a e power minus j omega squared. Okay. Now, this happens to be one of the Fourier transform pairs that we have to worry about. Notice that there is a Fourier transform pair in which we are asked to compute the time domain sequence of 1 over 1 minus a e power minus j omega squared. Okay, so I want to know how to solve that. So I want to give you a minute to think about it. It's actually very simple. You can apply the same principles that we have been looking at, and then we can compute. So let us say that this sequence is called x1 of n, some sequence x1 of n. Okay. Now, if I multiply x1 of n by a times x1 of n, what is the Fourier transform? It's going to be a divided by 1 minus a e power minus j omega whole squared. Nothing changed, only a scale factor multiplication. We are allowed to do that. Okay, and now I'm going to make one more change. I'm going to say I'm going to delay x1 by 1 unit of time. A times x1 of n minus 1. What will be the corresponding DTFT? Delay by 1 unit of time. You must multiply the discrete time Fourier transform by a exponential phase term e power minus j omega. A e power minus j omega divided by 1 minus a e power minus j omega squared. Okay, we are back to the original expression. If you compare 1 and 2, so 1 equals to 2. So the left hand sides of both 1 and 2, a times x1 of n minus 1 is equal to n times a of n u of n. Am I right? So basically we were trying to find out what x1 of n is, and so the first thing that we do is we can cancel this a, take it to the other side and make this n minus 1. Okay. So now we have come to a very simple step. If x1 of n minus 1 has you're given an expression, then how do you change it to x of n? So if you replace n with n plus 1, both left hand side and right hand side, then what you get is x1 of n will be equal to n plus 1 a power n plus 1 minus 1. So that will become a power n and u of n plus 1. N plus 1 a power n u of n plus 1. So from here we write down saying the sequence n plus 1 a power n u of n plus 1 is the sequence that will produce for us the discrete time Fourier transform 1 over 1 minus a e power j omega whole squared. So, we see that the results are related, but we can get variations in terms of the discrete time Fourier transform by doing simple transformations and applying it back to the result. So, two results from this: we have n a power n u of n, we have the DTFT. We also have the inverse DTFT of 1 over 1 minus a e power minus j omega whole squared. Okay, two things that we can take away from this particular result. So, using an existing Fourier transform pair, you can apply scale factors, you can apply delays in time, in frequency, both we can still use the ability to manipulate that. The other way that we understand is that whatever we used as a standard relationship can also be used as an inverse Fourier transform, because this is the calculation of the inverse. So, this is a calculation of the inverse Fourier transform. Okay. We can of course write down the expression integral minus pi to pi and all of that, but if you have a standard result, you can use the standard results to compute the inverse Fourier. So, this is the calculation of the inverse DTFT. Okay. So, the tables that we have studied have got very powerful applications. We can use them for modifying the sequences and getting new relationships, or we can use them to compute the inverse discrete time Fourier transform. Okay. Now, let us continue some very interesting examples ahead of us. Let us look at a property of convolution. Okay, example 4, the property of convolution. I am going to give you a very simple example so that we can appreciate the usefulness of this application. Now, if you have x1 of n equal to x2 of n, two sequences which are identical, they are both of them are 3-point sequences where the middle term is the origin. Okay. So, we can write down the corresponding relationship: x1 e of j omega is equal to x2 e of j omega equal to e power j omega plus 1 plus e power minus j omega. And what we are interested in is a calculation of the convolution of x1 of n with x2 of n. And this is something that we can write down just by inspection. The convolution of these two functions will be a triangular function which will start with value 1, go up to value 3 and then come down back to value number 1. This is the origin. So, 1, 2, 3, 2, 1, that's it's very easy for us to obtain numerically. Now, if it were a 20-point sequence, it would be extremely difficult for us to calculate this. Now, what is the application of the convolution theorem? The convolution theorem says that x1 of n convolved with x2 of n is equal to the product of these two, x1 e of j omega multiplied by x2 e of j omega. Okay, how do we do that? Very simple. We take these two expressions. We have the expression, so e power j omega plus 1 plus e power minus j omega multiplied by e power j omega plus 1 plus e power minus j omega. Okay, let's do the multiplication. So, multiplication with the first term, you get e power j 2 omega plus e power j omega plus 1. Okay, multiplication with the second term, use a different color, it is e power j omega plus 1 plus e power minus j omega. And multiplication with the third term, you get plus 1 plus e power minus j omega plus e power minus j 2 omega. Now, add all the three terms, you get e power j 2 omega plus 2 e power j omega plus 3 plus 2 e power minus j omega plus e power minus j 2 omega. Okay. Of course, from this we can derive that the sequence x1 of n convolved with x2 of n corresponds to 1, 2, 3, 2, 1 with the origin being at 3. Okay.